So hi everyone, my title is Preparation of Pure and Doped tin oxide for the detection of carbon monoxide gas by using the Sol Gel deep coating technique. From the title we can represent that I'm going to choose the tin oxide as a nanomaterial for the detection of CO gas by using the Sol Gel deep coating technique. For further enhancement of the sensing of gas sensitivity, I'm using the doped tin oxide for the detection of CO. First of all, let's go for the objective. In the objective, I'm just concentrating on the three part. First part, I'm just going to see the synthesis and characterization of pure and more noble metal dope thin oxide nanostructure by using the homogeneous precipitation method. And second thing, understanding and study and optimizing the structural, morphological and optical properties of pure and platinum dope thin oxide nanostructure. These are the second step. And the third important part is I'm going to investigate the CO gas sensing properties by sensing analysis by using the sensing parameters by using the sensing characterization technique. So all together, I'm just trying to take a one part of the chemical part, another part is electronic part. The electronic part, I'm just making the circuit by using the Arduino and other GSM module and Wi-Fi module. I'm just going to collaborate everything and make one prototype device for measure the two gases, CO and propane. This is my future work. So let's start with the introduction. First of all, why I choose this topic gas sensor. For example, just think in a day-to-day life, most of the products we use in day-to-day life are made in industries. Where in industries, it causes the causes of environment of toxic gases. Just imagine they are making some product or rubber or any kind of industrial products in a day-to-day life we use. These products have some kind of emission of gases. This emission of gases which got released outside the atmosphere, these gases which affects the human and affects the other persons in, for example, it causes lots of diseases. If you see in the image, you can see the different sources, for example, that the transport, the industries and factories and other sources which provides the gases, and the earth become totally full of toxic gases were surrounded by the people. So for example, the most important the gas source is, I can tell it's transport. Just imagine that the trucks, the cars and so many kind of vehicles which burns the fuel, maybe the petrol or diesel or gasoline or whatever, they just burn the fuel. It emits a range of health. It damages, it causes a pollutant. It provides a inflammable gases which causes the diseases. If you can see here, there is the various types of diseases which causes for the human. For example, the heart disease or lung disease is because of these inflammable toxic gases or hazardous gases. So this is the main thing which impressed me to choose this topic and work in the topic to make a smart city with providing the gas sensors in all over the places, like in the working areas, in the public and every places. So next, let me go for the working principle of gas sensing mechanism and the background of the gas sensing. The working principle is very simple. If you see, there is a nanomaterial here. When the oxidizing gas here, where the oxygen molecule is absorbed on the surface and which ejects the electron outside, so there will be the no flow of electrons. While the reducing gas agent which injects the electron, there will be the flow of electrons. Due to this flow of electron, we can measure the gas sensing. So these are the two types. For example, imagine that it is in the pure air. In clean air, the donor electron in the metal oxide are attracted towards oxygen, which is observed on the surface of the sensing material, while the electronic flow will be low. In the process of the reducing gas, the surface density with absorbed oxygen will decrease. As it reacts with the reducing gases, the electrons will be released into the electron will be released into the metal oxide, and there will be electron flow. This flow can be measured by the sensor. So this is the basic working principle. If you see in the image, there when the electron will be ejected outside, there will be a depletion region. Because of this depletion region, the gases cannot be flow. This depletion region is also called as a Schottky barrier. When the Schottky barrier is high, there will be no sensitivity, no enhancement of sensitivity. When during the reducing gases CO2, the Schottky barrier will be get reduced, so the while the electrons can be flown so freely, so that we can measure the sensitivity of the carbon monoxide gas or any other hazardous gas. It's simple that the reducing gas agent will inject the electrons, while the oxygen in the atmosphere which ejects the electrons. The inject the electrons which gives a flow of electron. These flow of electron which provides the measurement of the sensitivity in the gas sensor. While here the grain plays an important role, as I say, the grain size is important. For the grain size, if the grain size is very small, the electron flow will be good. If grain size is big, there will be more depletion region. So in that case only we have to do the band widening or high temperature. We can just tailor the material to have a small grain size. Let's go for experimental detail. In experimental detail, I have just made a synthesis of tin oxide nanomaterial. Before I go to tin oxide nanomaterial, I have to know why metal oxide, why I choose metal oxide for gas sensor. The metal oxide gas sensor, it is very effective, and it has a good physical and chemical properties compared to the other materials. It is very effective for the interaction with the targeted molecule. It is for selectivity. If, for example, the CO or propane, we have to select the particular gases, the metal oxide is the best choice for the gas sensing. The metal oxide can be even tailoring surface property of metal oxide, which allow impressing sensing properties, and metal oxide is very low, and with a low cost it gives a high sensitivity. That's why the metal oxide is best for the gas sensing mechanism. Where the gas sensing have a different kind of properties like sensitivity, selectivity, and stability, and these are the properties which gives an important role for the metal oxide semiconductor. In metal oxide there are different types of metal oxide. For example, the zinc oxide, tin oxide, and various metal oxide. While I choose tin oxide because it has a good band gap, and it is a transparent conductivity material. It gives a more conductivity flow of electrons, while the reducing gas agent reacts with the tin oxide, and that's why I choose tin oxide. And the oxides are good for transparent material. That's why the transparent material is tin oxide material. So that's why I choose tin oxide material. If you see here, I just first synthesis of tin oxide material by using the tin acetate and water. I make a solution 1, and I'm making the sodium hydroxide and methanol as a solution B, and mixing together and stirred in a certain temperature, and I form the solution and calcinated at the 600 degrees Celsius for 2 hours, and finally I just made a swirl gel method to get a liquid kind of a tin oxide and just place aside. And right now here the dip coat technique is used. I'm just taking the glass, a particular small piece of glass, I'm just dipping in the tin oxide solution, and I'm just dipping 2 times, it's called as a 2 layers, and I'm just making another composition 4 times, it's called as 4 layers tin oxide dipping. Vice versa, I'm just taking these 2 tin oxide glasses and I'm just dipping into the silver solution. As like same there, 2 layers and 4 layers, I'm just dipping 2 times and 4 times the silver oxide dip and calcinated and dried in a certain temperature. So I got the totally the 4 composition of tin oxide, and the doped silver doped tin oxide is ready. So right now let's go for the results and characterization. In the result, first I'm just going for the XRD. The XRD index in XRD, it shows that the peaks here, the 101 and 101, 110, 101, and these are the peaks which shows that the tin oxide is formed. While the tin oxide, the following peak 110, 101, 200 are reported value of tin oxide in JCDPS. The crystalline size was calcined by using the Derbyshire equation, and the crystalline size is 8.95 nanometer. And even it explains the tetrahedron rutile crystalline phase of tin oxide. If you see here, there is a three kind of graphs which is in different temperatures: 600-degree temperature, 700-degree temperature, and 800-degree temperature, which was different types, 4 times and 10 times. It means that I just made a centrifugal to get the peak without a noise. So I was doing a research to get a good peak of XRD. So in the next slide, I'm just showing the sensitivity characterization for the sensitivity of tin oxide with a 2-layer and 4-layer. If you see, the response change depends upon the temperature. At a particular temperature, we get a maximum result. For example, if you see here the 200 degrees Celsius, it shows the maximum result in 2-layer. In 4-layer, it shows a high sensitivity. Compare 100 ppm, 100 degree, it shows a 200 degrees temperature has a high sensitivity. In vice versa, the sensitivity of tin oxide with the 2-layer with a doped tin silver doped. If you see here, the 300 degree shows a high sensitivity, while in the 4-layer have compared to that 2-layer, the 4-layer have a more sensitivity compared to that silver doped tin oxide 2-layer. So since the gas concentration increases, the number of atoms are observed on the sample surface. The increased electrical conductance, while for example the gas conductance or more the gas concentration increases, the number of atoms will get absorbed on the material, where the electrons will keep on injecting on the surface. Due to that, the electron flow will be keep on increasing. So in that case, the sensing enhancement will be increased and selectivity will be get increased. So while we can measure from overall, we can see that the tin oxide show a sensitivity, a good sensitivity, but the silver doped tin oxide which shows a better sensitivity compared to the metal oxide semiconductor. When we compare the results of pure tin oxide and silver tin oxide nanometer, doped metal oxide show more sensitivity to operating temperature and the concentration of CO gas. After I measure this is the second step of the project. I'm just making a circuit device by using the three components: the Arduino, the GSM module, and the two sensors with the different material. While in future, I'm just implementing with my tin oxide nanomaterial with all these sensors. This is a Wi-Fi module, this is a GSM module, and this Arduino which is connected, and I just connected with my computer. I'm just using the Arduino C++ interface programming to make the gas measurement. So when the gas reacts with these sensors, it gets a certain kind of sensitivity, and it sends a message to my mobile phone by using the GSM module, and even sends email by using the Wi-Fi module. So this is a circuit implementation with a GSM module. In further future, I just make two materials and implemented with that for the two gases, CO and propane. This is my further future work. So finally, I conclude that the tin oxide structure is formed successfully, and the crystalline size is 8.95 nanometer. And the sensing characterization are measured in various temperature, 100 to 3 degrees, and shows enhanced selectivity and sensitivity in silver doped tin oxide. And Arduino Uno was used to collect the data, and the GSM module was also used for the wireless transmission. Finally, I want to thank you for giving this opportunity to present my poster in this event, and thanks to my supervisor Dr. Marillo and Dr. Maldonado, and I'm thanking my co-supervisor Chandrila Karthik for helping and guiding me in all the sources, and I'll thanks my lab assistant Miguel Luna for helping in the lab for the sensing characterization. And finally, I wish to thank CONACYT for funding for my project and supporting me. Thank you. For contact me in the email, the govan.panil@srinivastam.mx. Thank you.